Ferrero Rocher is the most luxurious chocolate in the world, but behind the gold wrapper lies a factory process few ever get to see. From hazelnut selection to precision layering and flawless golden packaging, every Ferrero Rocher is engineered with obsessive detail. In this documentary, we uncover how Ferrero Rocher is really made and reveal the hidden complexity behind every bite of this iconic chocolate. The journey to create a Ferrero Rocher begins long before any chocolate is tempered or gold foil is wrapped. At its heart lies a hazelnut, and not just any hazelnut. Ferrero sources its hazelnuts primarily from its own agricultural subsidiaries across Italy, Turkey, Chile, and the United States, maintaining vertically integrated supply chains. The factory only uses specific cultivars with a consistently round shape, low moisture content, and a rich, buttery flavor profile. These hazelnuts are known for their roasting performance and uniformity, which are critical in a process that scales to millions of pieces per day. Upon arrival at the production facility, the hazelnuts are unloaded from sealed food-safe bulk containers and moved directly into raw material intake silos. These silos are temperature and humidity controlled to prevent moisture absorption or rancidity. Before they're accepted into the main line, samples from every incoming batch are tested in the factory's on-site lab. Here, chemical composition, size, oil content, and shell integrity are measured. Random nuts are dissected and inspected for mold, aflatoxins, or insect damage. Only batches that meet Ferrero's strict tolerances pass through to the next phase. After intake, hazelnuts go through an intensive cleaning and sorting phase. Pneumatic air classifiers remove light foreign material like leaves or twigs, while vibratory sieves and optical sorters remove undersized, broken, or discolored nuts. The next step is roasting, a critical transformation stage that dictates the final flavor of the entire chocolate. The factory uses continuous belt roasters or fluidized bed systems that allow precise control over temperature and airflow. The hazelnuts are roasted at temperatures between 140 degrees Celsius and 160 degrees Celsius for 15 to 25 minutes, depending on moisture content and target flavor development. The roasters are outfitted with inline sensors that continuously monitor temperature, kernel color, and weight loss. Each nut is tracked by its lot number, and roast profiles are tailored to each batch to ensure consistency. Once roasted, the hazelnuts are cooled rapidly using forced air cooling systems to prevent over-roasting and to stabilize the oils. The now crispy skins are loosened during roasting and are removed in large-scale abrasive peelers, machines that spin the nuts against fine-textured rubber belts, stripping away the skins without damaging the core. At this point, a percentage of the roasted, peeled hazelnuts are set aside for whole use. These will eventually form the central core of each Ferrero Rocher, but the majority are transported into grinding and blending stations for the creation of Ferrero's ultra-smooth Gianduja-style filling, which sits just beneath the shell. The nuts designated for filling are passed through industrial conching grinders. These high-speed systems generate heat through friction, reducing the hazelnuts into a fine paste known as hazelnut butter. The paste is blended with powdered sugar, milk solids, cocoa powder, and a small amount of vegetable oil to create the silky, nutty filling that defines the brand. The consistency of this hazelnut cream must be exact. Viscosity is measured continuously using inline viscometers, while fat content and particle size distribution are tracked in the lab. The filling needs to remain soft and pipeable at controlled temperatures, but must also resist oil separation over its shelf life. To achieve this, Ferrero employs emulsifiers and stabilizers, but in meticulously optimized concentrations, ensuring that the flavor of the nuts remains dominant while the texture holds up over time. The finished filling is held in jacketed stainless steel tanks with gentle agitation to keep it homogeneous. These tanks are connected to piping systems that lead to the next station, center formation. This is one of the most mechanically intricate parts of the Ferrero Rocher manufacturing process. A specialized depositor machine injects a portion of the hazelnut cream into preformed chocolate wafers, while simultaneously placing a whole hazelnut directly into the center. These wafers are precision-molded hemispheres, delicate yet structurally rigid enough to hold filling without cracking. The depositor head works at high speed, aligning cream, hazelnut, and wafer half shell in one synchronized motion. Once filled, two hemispheres are pressed together with precise pressure and rotation to create a sealed, spherical core. The seam is smoothed by a heated rolling chamber, which blends the edges of the wafer halves together, using just enough thermal energy to fuse without over-softening. At this stage, the product is still structurally vulnerable, so it is immediately transferred to a cooling zone. In this controlled tunnel, ambient temperature is gradually reduced to stabilize the hazelnut cream and harden the wafer shell. Airflow is carefully directed to prevent condensation or uneven cooling. The spheres are rotated during cooling to maintain shape and uniformity. With the fragile hazelnut-filled spheres now stabilized after cooling, the next phase of Ferrero Rocher's industrial creation process moves into what may be its most visually iconic stage, the chocolate coating and enrobing line. Here, the spheres are transformed from delicate, pale wafer-based cores into gleaming orbs of textured chocolate and crushed hazelnuts. This phase demands tight control over temperature, viscosity, and timing, requiring highly specialized machinery to create the exact visual and sensory texture Ferrero is known for around the world. The first step in this phase is called pre-coating. Before applying the outermost layer of chocolate and hazelnut granules, the wafer spheres must be sealed in a protective chocolate coat that both strengthens the structure and acts as a moisture barrier. The wafer shell, while crisp and delicate, is porous and hydrophilic, meaning that without a sealed layer of fat-based coating, it could absorb moisture from the surrounding air or filling and go soft. To prevent this, the cooled spheres are conveyed into a rotary enrobing drum. This drum is a rotating stainless steel barrel with angled internal fins. It slowly tumbles the spheres while fine jets of tempered chocolate are sprayed from nozzles arranged in concentric rings. This chocolate, made from a proprietary blend of milk solids, cocoa butter, cocoa liquor, and sugar, is pre-tempered to ensure crystallization structure, gloss, and a smooth mouthfeel. The chocolate is pumped from a heated reservoir kept at a strict 31 to 32 degrees Celsius, the ideal working range for enrobing milk chocolate. As the spheres tumble through the drum, the thin spray of chocolate coats them evenly. The rotation ensures every surface is touched without allowing pooling or excessive buildup. Each sphere passes through this drum for approximately 15 to 20 seconds, enough time for full coverage, but short enough to avoid heat penetration that might soften the core. Once coated, the spheres move immediately into a cooling tunnel, a long, gradually chilling corridor where the chocolate layer is allowed to set. This tunnel maintains an ambient environment of 10 to 12 degrees Celsius with less than 50% humidity, ensuring the chocolate hardens smoothly and with the correct crystalline form. Next comes one of Ferrero Rocher's most defining sensory features, the rough, nutty exterior. To create this, the cooled, pre-coated spheres are passed through a second enrobing station where they receive a final coating of chocolate mixed with crushed roasted hazelnut fragments. This mixture is stored in a jacketed mixing kettle that gently stirs it to keep the nut pieces evenly suspended in the chocolate. The chocolate itself is slightly more viscous than the pre-coat formulation, engineered to hold the heavier particles in suspension while still flowing smoothly over the spherical surfaces. At this enrobing station, the spheres pass under curtain-style chocolate waterfalls, controlled flows of chocolate hazelnut mixture that cascade down over them as they move along a vibratory conveyor belt. As each sphere receives this layer, it is gently rocked back and forth to distribute the coating evenly and prevent accumulation on one side. Immediately afterward, the coated spheres pass beneath precision air knives, thin, high-velocity streams of air that remove excess chocolate while preserving the textured, lumpy appearance of the nut coating. The airflow is adjusted based on real-time feedback from load cells, measuring the weight of sample pieces exiting the line. This final chocolate nut layer adds both crunch and the brand's signature visual finish. But just like the first chocolate layer, it must be rapidly and precisely cooled to lock in the texture and prevent bloom. The coated orbs enter a second cooling tunnel, this one longer than the first and broken into multi-zone chambers. Each chamber reduces the temperature by a few degrees, beginning at around 18 degrees Celsius and dropping to as low as 7 degrees Celsius by the end. This stepped cooling helps avoid thermal shock, which could crack the chocolate or cause the wafer interior to become brittle or absorb ambient moisture. Once fully set and stabilized, the finished chocolate spheres proceed to the final phase, the wrapping line. Unlike traditional bar-shaped chocolates, Ferrero Rocher's spherical format poses significant challenges for automated packaging. Each sphere must be individually wrapped in gold foil, creased along symmetrical lines, and sealed at the base, all without crushing or distorting the fragile chocolate shell. To accomplish this, Ferrero's wrapping system utilizes a series of robotic arms equipped with soft grip silicone actuators. These arms pick up individual spheres from the end of the cooling line and place them into pre-cut sheets of gold foil resting on vacuum-assisted form trays. Each foil sheet is statically charged to slightly lift its edges, allowing the robotic arm to nest the chocolate sphere into its center without displacement. Once placed, a mechanical rose press spins and crimps the foil around the sphere using concentric rotating plates, applying precise pressure to form clean, flower-like folds without damaging the surface. This wrapping process is performed at high speed, up to 300 pieces per minute, yet with micron-level accuracy. Foil alignment is verified by optical sensors, which detect reflective patterns and reject any pieces where the foil is torn, off-center, or folded incorrectly. Each wrapped sphere is then carefully lifted into a pleated paper cup, embossed with the Ferrero logo and treated with a micro-wax lining to keep it crisp and grease-free. After wrapping and cupping, the products pass through final quality inspection stations. Here, high-resolution cameras inspect every sphere for uniformity in size, foil fold consistency, and cup placement. Variations as small as 0.5 millimeters in height or misfolds in the foil pattern trigger automatic rejection and rerouting for manual inspection. Ferrero places high value on uniform appearance, as the product is both a confection and a visual symbol of luxury. At this stage, the chocolates are grouped and placed into clear plastic domes or rigid paper boxes, depending on SKU. Grouping is done by programmable robotic arms that align pieces into the iconic pyramid-shaped trays. Each tray is inserted into branded secondary packaging by automated folding arms, heat-sealed, labeled with batch codes and best before dates, and packed into master cartons for shipping. These cartons are then palletized, shrink-wrapped, and barcoded for traceability using a fully automated warehouse system. Once the Ferrero Rocher chocolates are fully enrobed, wrapped, cupped, and packed into their respective trays and branded packaging, they enter a post-production system that is every bit as engineered and precise as the stages that crafted them. This final section of the industrial manufacturing process focuses on how Ferrero ensures product longevity, freshness, safety, and global delivery, all while adhering to strict standards for sustainability, food safety, and visual uniformity. It is in this post-production phase that every element of quality assurance, logistics, and environmental control plays a crucial role in maintaining Ferrero Rocher's globally recognized consistency. At the end of the packaging line, finished boxes are conveyed into an area known as the atmospheric control and shelf stability checkpoint. This isn't merely storage, it's a climate-controlled stage designed to lock in freshness and prevent any deterioration before shipping. Although Ferrero Rocher does not require refrigeration, its chocolate and hazelnut content are sensitive to heat, humidity, and oxygen exposure. Thus, the packaging process incorporates passive and active protective methods. Each individually wrapped Ferrero Rocher sits in a waxed paper cup and is sealed with foil, creating a light barrier and reducing oxygen transfer. On a boxed level, the packaging is designed not just for aesthetics, but for product protection. The plastic domes and rigid cartons serve as microenvironments, shielding the delicate chocolates from moisture migration and aroma contamination. Many of these boxes are nitrogen flushed prior to sealing. This involves replacing the oxygen inside the packaging with food-grade nitrogen gas. The process is conducted in a low-oxygen chamber using automated nozzles that inject nitrogen and heat seal the package in one fluid motion. This significantly extends shelf life and prevents oxidation of the hazelnut oils, which could otherwise lead to rancidity over time. Inside the post-packaging facility, all finished goods are held in a fully climate-controlled warehouse. The temperature is maintained between 12 degrees Celsius and 18 degrees Celsius with strict humidity control to avoid condensation or water activity that could degrade the chocolate or cause surface bloom. This facility is divided into inventory zones based on SKU, destination, and production date. Robotic pallet stackers and AGVs move products from the end of the line to designated storage lanes, which are connected to real-time digital inventory systems. Each pallet is barcoded and tracked with RFID tags linked to Ferrero's MS. This allows precise location tracking within the warehouse and connects the pallet's ID to batch-level data such as production shift, ingredient lot numbers, and inspection records. If a quality control concern arises, even weeks after production, the system can trace every individual chocolate back to the exact time, machine, and ingredient batch from which it originated. From this stage, logistics planning takes over. Ferrero Rocher products are shipped globally, and the logistics operation must ensure that every box reaches retailers in optimal condition, regardless of climate or shipping duration. For international exports, especially to regions with high ambient temperatures, insulated shipping containers or refrigerated trucks are used. These containers are monitored with onboard thermal sensors that log temperature data every few minutes throughout the journey. To minimize risk and ensure transport resilience, Ferrero's logistics systems include contingency protocols. If any deviation is recorded, say, a rise above 22 degrees Celsius for more than 2 hours, alerts are sent to distribution managers, and the shipment is flagged for secondary inspection upon arrival. If chocolate is exposed to unsafe temperatures, it may still appear intact, but could be structurally compromised or display bloom later. As such, these shipments are not automatically released and instead undergo retesting at the receiving distribution center. Distribution centers, whether owned by Ferrero or contracted third-party logistics partners, follow a standardized intake protocol. Every incoming shipment is verified against temperature logs and visual condition before being moved into inventory. Sampling is done on arrival. Inspectors randomly open retail cartons, remove individual Ferrero Rocher pieces, and subject them to quick checks for foil adhesion, paper cup deformation, and chocolate bloom. Any deviation from norm triggers a full line hold and a report to Central Quality Assurance. On a broader scale, Ferrero monitors product life and performance with a shelf life prediction algorithm that uses environmental exposure data, production variables, and regional velocity analytics. This allows the company to adjust shelf life claims and shipping cycles based on real-world data, rather than relying solely on laboratory simulations. It ensures that when a consumer opens a box, even after 8 to 10 months of storage, the product tastes and looks nearly identical to one fresh from the line. Simultaneously, efforts are being made to reduce the environmental footprint of this entire extended production ecosystem. Ferrero has pledged to reduce plastic use and improve packaging recyclability across all its product lines, and Ferrero Rocher is a major focus area. The familiar clear dome packaging, though attractive, is being redesigned with sustainability in mind. Research is underway to create bio-based plastic alternatives or entirely recyclable paperboard structures that still offer the same clarity, structure, and product visibility. On the energy front, the manufacturing facilities are increasingly integrating renewable energy sources. Solar panels are being added to plant rooftops, and waste heat from the roasting process is now recaptured through heat exchangers and reused in washdown systems or air heating coils. Motion sensing LED lighting, closed-loop water filtration systems, and advanced waste separation at the plant level ensure that the high-end nature of the product does not equate to unsustainable production. Even the Hazelnut supply chain is now being restructured with long-term sustainability in mind. Ferrero's Farming Values Initiative works directly with hazelnut growers to implement traceability systems, promote biodiversity, and reduce reliance on synthetic inputs. Satellite data is now used to track soil health and pest pressure in real time, helping farmers reduce chemical usage while ensuring yield. These practices not only improve the environmental profile of the product, but directly contribute to the flavor consistency that is so critical to Ferrero Rocher's sensory identity. Finally, the company maintains a feedback loop from the consumer level all the way back to the manufacturing floor. Customer complaints or praise received via QR codes, customer service centers, or digital platforms are fed into an AI-powered insights platform. This system identifies emerging patterns, be it foil issues in a certain geography or flavor feedback in a seasonal SKU, and flags them for product review. If an actionable issue is identified, it can prompt retraining, supplier audits, recipe reformulation, or machine recalibration, depending on severity. Every step in Ferrero Rocher's journey, from the raw hazelnut fields in Turkey to the moment a box is opened during a celebration, is built on a foundation of precision, care, and control. It is a product that feels artisanal in experience, yet is undeniably industrial in scale. What emerges from Ferrero's vast, data-driven, sensor-monitored facilities is a confection that combines the warmth of tradition with the cold logic of automation, creating a gold-wrapped chocolate that is as technically impressive as it is delicious. Innovation, refinement, and global adaptation form the final layer of Ferrero Rocher's manufacturing ecosystem. While its iconic gold-wrapped hazelnut chocolate remains a symbol of indulgence and celebration, Ferrero's factories are far from static. Instead, they operate as dynamic, research-driven environments where new ideas are tested constantly, whether that's refining texture, adjusting to new market preferences, or introducing entirely new product variations. Behind every Ferrero Rocher lies not just tradition, but a relentless cycle of experimentation, data collection, and global customization. One of the most important hubs within any Ferrero Rocher facility is the Research and Development Laboratory. Here, food technologists, chocolate scientists, and texture engineers work year-round on small batch prototypes. These labs are equipped with micro roasters, pilot-scale enrobing machines, miniature tempering units, and lab-grade sensory booths. This allows for full-scale simulations of production on a fraction of the scale, enabling rapid prototyping without disrupting live manufacturing lines. One area of constant experimentation is the texture of the hazelnut cream filling. While the classic Ferrero Rocher contains a smooth, nut-forward gianduja-style filling, consumer trends in some markets have shown preferences for creamier, milkier textures, or ones with inclusions such as wafer crisps, puffed rice, or even salt crystals. To adapt, R&D teams run side-by-side tests on fat ratios, alternative nut varieties, and natural emulsifiers. They analyze viscosity curves using rheometers and conduct accelerated aging studies to evaluate how texture changes over time under various storage conditions. R&D also works on flavor innovation. Though the classic Ferrero Rocher flavor is universally recognized, limited editions and regional exclusives are critical for keeping consumer interest fresh in high-growth markets. For example, in parts of Asia, Ferrero has tested matcha-infused chocolate coatings. In Latin America, dulce de leche fillings have been trialed. In the Middle East, formulations involving pistachio or rosewater flavor notes have been prototyped. Each of these requires adjustments, not just in recipe, but also in process. Certain fillings require higher thermal tolerance, others may react differently during enrobing or wrapping due to their moisture content. To ensure quality and consistency, each proposed variation undergoes extensive testing in the factory's sensory evaluation chambers. These are specially designed, soundproofed booths lit with neutral lighting, where trained panelists assess everything from first bite crunch to flavor release, melt rate, and aftertaste. They score samples against a range of criteria: intensity, balance, mouthfeel, appearance, and compare them to the gold standard classic product. Panelist feedback is digitized and overlaid with analytical data such as fat bloom index, water activity, and melt point curves to determine feasibility. Once a prototype passes internal tests, it must also be validated for scalability. Some ingredients or formulations work beautifully in the lab, but fall apart at industrial speeds or under prolonged storage. For example, softer fillings may leak during high-speed rotation, inclusions may settle unevenly during conveyor vibrations, or certain coatings may discolor during heat sealing. The pilot line, an intermediate-sized mock-up of the full production line, is used to model these issues before any full-scale commitment is made. Beyond taste and texture, the factories must also accommodate aesthetic variations. Ferrero Rocher is synonymous with visual perfection. For seasonal lines like Ferrero eggs, Valentine's hearts, or Easter nests, new mold tooling, wrapping foil textures, and carton formats must be developed. These new shapes aren't merely cosmetic. They change the product's center of gravity, its cooling requirements, and its wrapping dynamics. Engineers run simulations using CAD software and finite element modeling to ensure each new format can be safely and efficiently molded, coated, cooled, and wrapped without jamming or deformation. Each new mold also undergoes cycle time testing, measuring how many pieces per minute can be output while maintaining perfect quality. The aim is always to balance aesthetics with operational feasibility. For instance, a limited edition rose petal texture on the outer shell may look beautiful, but if it causes inconsistent wrapping folds or snags in the packing machine, it will be rejected or redesigned. Beyond internal product development, Ferrero Rocher factories must also localize production to suit regional regulations and consumer expectations. In some markets, ingredient restrictions may prohibit certain emulsifiers, sweeteners, or dairy derivatives. In others, there may be stronger demand for plant-based, organic, or clean label products. For example, factories supplying Northern European markets must comply with stricter labeling laws regarding palm oil and genetically modified ingredients. Ferrero addresses this with modular ingredient silos, and real-time formulation control, switching between regional recipe variants without needing to rebuild entire lines. Chocolate begins its life not in the factory, but on the tropical cacao farms that line the equator. These farms are located in countries across West Africa, Central and South America, and Southeast Asia, with Ivory Coast and Ghana among the world's top producers. The climate in these regions, hot, humid, and with rich, well-draining soil, is essential for the cultivation of Theobroma cacao, the tree that produces cacao pods. Each pod contains 20 to 50 seeds, known as cacao beans, surrounded by a sweet, pulpy, white fruit. These beans are the raw foundation of all chocolate products. The cacao harvest is entirely manual. Farmers use machetes or curved knives attached to long poles to carefully cut ripe pods from the trees without damaging the branches. A single mature tree may produce between 20 and 30 pods per year, and since cacao does not ripen all at once, harvesting occurs continuously over several months. Once harvested, the pods are collected in piles and opened by hand using machetes. The beans, still coated in sticky white pulp, are scooped out and prepared for fermentation, the first transformative step in the chocolate-making process. Fermentation typically occurs on the farm or at centralized collection centers. Though it might sound like a simple resting period, fermentation is a critical and highly sensitive step that chemically alters the beans and begins to develop the flavor precursors of chocolate. Beans are placed in shallow, slatted wooden boxes or piled into heaps and covered with banana leaves. This environment encourages the growth of natural yeasts and bacteria that convert sugars in the pulp into alcohol and acids. As the temperature rises, often reaching 45 to 50 degrees Celsius, the bean's internal structure changes. Enzymes are activated, cell walls are broken down, and bitter polyphenols begin to transform into the complex flavor compounds that will later give chocolate its signature taste. Fermentation typically lasts 5 to 7 days, during which the beans are turned or mixed once or twice a day to ensure even microbial activity and oxygenation. This step is closely monitored, as under-fermentation leads to bland or vegetal flavors, while over-fermentation can introduce off notes like mold, vinegar, or excessive bitterness. Many large chocolate manufacturers, even though they don't ferment beans on site, have established quality programs with their cacao suppliers, training them in fermentation control, and even requiring on-site testing of pH and temperature during the process. Once fermentation is complete, the beans are spread out to dry. Drying can be done on large tarpaulins, bamboo mats, or raised wooden platforms under the sun. Industrial cacao processors often prefer sun drying, which can take 5 to 10 days, as it produces cleaner, more natural flavor profiles. During drying, the beans are turned regularly to ensure even moisture loss. The goal is to reduce the moisture content to around 6%, 7%, a safe level that prevents mold and microbial growth during storage and transport. At this point, the beans are still covered in their thin, brittle shells and have taken on a dark brown color, with their signature earthy, chocolatey aroma starting to develop. The beans are carefully bagged in burlap sacks, usually 60 to 65 kilograms per bag, and labeled with origin information including country, region, farm or co-op, and processing dates. These bags are then consolidated for export. Exporting cacao beans requires extreme care and logistics planning. Moisture, heat, and exposure to foreign odors can degrade the beans before they even reach the factory. To prevent spoilage, the sacks are loaded into dry, ventilated shipping containers, often lined with insulating material or desiccant packs to control humidity. During long overseas shipments, particularly by sea freight, the cargo is monitored using data loggers that track temperature and humidity. If the beans are exposed to extreme conditions, entire shipments can be rejected by the receiving chocolate manufacturer. When the beans arrive at the chocolate factory, Usually located in Europe, North America, or Asia, they undergo a rigorous intake and inspection process. This is where industrial chocolate production truly begins. First, the bags are unloaded into a receiving area, where samples are drawn from each lot and taken to the quality control lab. Here, technicians measure moisture content, check for mold or insect damage, and grade the beans based on size, color, and cut tests. Cut tests involve slicing a sample of beans lengthwise and examining the cross-section. Properly fermented beans will have a uniform, slightly purplish interior with no signs of germination or off colors. Beans that meet the manufacturer's standards are then approved for processing. The sacks are emptied into large hoppers that feed the cleaning and pre-processing line. At this point, the factory begins to function much like a grain mill, sorting, cleaning, and prepping the raw material for transformation. The first stage is mechanical cleaning. The beans pass through vibrating screens and air jets that remove sticks, stones, dust, string, and other foreign materials. Magnetic separators remove any stray metal particles picked up during harvest or shipping. After cleaning, the beans are often sorted by size. This is an optional step, but many high-end chocolate makers insist on sorting to ensure that beans of uniform size are roasted together. Uneven roasting is a major risk if large and small beans are mixed, as the small beans may burn while the larger ones under-roast. Before roasting, the factory may also conduct a dehumidification step, particularly if the beans arrived slightly above target moisture. Large rotary dryers or low-temperature ovens are used to bring the beans into precise moisture range, often 5%, 6%, to prepare for optimal roast conditions. This is all monitored through programmable logic controllers that track time, temperature, airflow rate, and moisture loss in real time. With the cacao beans now thoroughly cleaned, dried to precise moisture levels, sorted by size, and passed through rigorous quality inspections, the chocolate production process enters one of its most transformative and delicate phases: roasting. This step marks the moment when raw agricultural product begins to develop the hallmark sensory properties of finished chocolate: aroma, depth, bitterness, sweetness, and complexity. Far from being a simple baking process, industrial chocolate roasting is a finely tuned science that must balance heat, time, air circulation, and even bean origin to unlock the flavor potential locked within the bean's cellular structure. The roasted profile of chocolate is not one size fits all. It varies greatly depending on the origin of the beans, the desired flavor profile of the final product, and the style of chocolate being produced, whether it's milk, dark, or even single origin specialty bars. As such, chocolate factories have roasting protocols tailored to each bean variety and product type. These protocols are logged as roast profiles, charts that map temperature over time, often broken into phases: drying, browning, and development. Each phase requires precise thermal input and airflow to extract the right flavors without burning or flattening the bean. Industrial chocolate factories use several types of roasters depending on scale and product goals. The most common are batch drum roasters and continuous roasters. Batch drum roasters, similar in design to coffee roasters but much larger, feature a rotating cylindrical drum made from stainless steel. Beans are loaded into the drum, which rotates over direct or indirect heat, with hot air circulated through the drum chamber. Temperature sensors embedded in the drum monitor the bean mass, ambient air, and exhaust temperatures simultaneously. Factory operators can adjust drum speed, airflow rate, and burner intensity through PLC-controlled interfaces to manage the roast curve. Roasting typically begins at a lower temperature, around 100 degrees Celsius, to drive off any remaining surface moisture. This is the drying phase and usually lasts for 5 to 10 minutes. The beans then enter the browning phase, where the Maillard reaction begins. This is the chemical process that causes amino acids and reducing sugars in the beans to recombine and form hundreds of flavor compounds: nutty, roasted, caramelized, and acidic notes that are essential for chocolate's complexity. This phase is carefully controlled, usually taking another 10 to 15 minutes, with bean temperatures rising to 120–140 degrees Celsius. The final stage of roasting is known as development, or the finishing phase. Here, the beans are brought to their final internal temperature, typically between 135 degrees Celsius and 150 degrees Celsius, depending on the desired flavor profile. This phase is brief, often just 2 to 5 minutes, but it's critically important. Too little development, and the flavor may be grassy or underwhelming. Too much, and the chocolate may taste burnt, acrid, or flat. Advanced factories use real-time infrared cameras and bean temperature probes to monitor this phase with incredible accuracy, sometimes recording temperatures at 1-second intervals. After roasting, the beans must be cooled quickly to halt the cooking process. This is usually achieved in a dedicated cooling drum or tray system, where ambient or chilled air is blown across the beans using high-speed fans. Cooling not only stops the roast, but it also firms up the bean shell and prevents steam buildup, which could cause condensation or spoilage during storage. At this point, the beans are dark brown, fragrant, and brittle, but they still contain their outer shells, a thin, papery husk that must be removed to access the valuable interior, the cacao nib. The next phase is known as winnowing. Winnowing is a mechanical process that cracks the beans open and separates the lightweight shells from the dense nibs using a combination of crushing and air classification. In a large-scale chocolate factory, beans are first passed through a pre-cracker or roll crusher, which breaks them into fragments of varying size. The cracked mixture is then fed into a winnowing chamber, often a series of vertical air columns or vibrating conveyor belts, where calibrated air jets or suction systems separate the heavier nibs from the lighter shells. The airflow is precisely tuned so that the nibs fall to the bottom collection bins while the husks are drawn upward into separate waste hoppers. The result is a batch of pure cacao nibs, dark, rich, and packed with flavor and cocoa solids. These nibs are now ready to be transformed into chocolate liquor, not an alcoholic beverage, but a thick, paste-like substance made from finely ground cacao nibs. This is where the chocolate truly begins to take shape. To produce liquor, the nibs are passed through industrial grinders known as pre-refiners or impact mills. These machines use either rotating steel blades or stone rollers to shear the nibs into smaller and smaller particles. As the nibs are ground, frictional heat causes the cocoa butter inside to melt. This transforms the mixture from a coarse, gritty powder into a flowing paste with a smooth, velvety texture. The grinding process typically reduces particle size to around 80 to 100 microns during this first stage. From here, the liquor is either held in heated tanks for further processing or sent directly to the next grinding phase, refining. Refining is the step where particle size is further reduced to achieve the smooth mouthfeel expected from high-quality chocolate. This is performed using 5-roll refiners or ball mills. 5-roll refiners consist of 5 horizontally stacked steel rollers, each rotating at a different speed. The chocolate liquor is fed into the gap between the rollers, which progressively shear the particles down to between 15 and 25 microns. At this size, individual cocoa and sugar particles are too small for the tongue to detect, giving chocolate its creamy texture. In factories producing sweetened chocolate, sugar is added during this refining phase. The sugar, already pre-milled to ensure consistent granule size, is blended with the chocolate liquor to form what's called a chocolate crumb. Depending on the recipe, milk powder, vanilla, lecithin, and other ingredients may also be added at this stage. These additions are carefully weighed and dosed using automated batching systems, which ensure that every batch conforms to a master formulation. After refining, the chocolate mass still feels dry and powdery. To turn it into a cohesive, pourable liquid with a smooth finish and stable flavor, it must undergo conching, a prolonged mixing and aeration process that can last anywhere from several hours to multiple days. Conching takes place in large heated vessels fitted with rotary arms or heavy granite rollers. The goal of conching is threefold: to develop flavor by oxidizing volatile acids, to smooth texture by distributing fat uniformly, and to improve viscosity by reducing moisture and undesirable compounds. The conching process is controlled in phases: dry conching, where the paste is crumbly and thick; plastic conching, where it softens and flows; and liquid conching, where the mass becomes fully fluid. Each conching profile is custom tailored to the specific chocolate type being produced. Milk chocolate, for instance, requires longer conching to balance milk solids and sugars, while high percentage dark chocolate may be conched shorter to retain more of its natural acidity and origin flavor. Throughout conching, temperature, shear force, and oxygen flow are all regulated. Some factories utilize closed-loop conchers with nitrogen blanketing to reduce oxidation, while others incorporate vacuum systems to pull out undesirable volatile compounds. This stage is monitored using inline viscometers and gas sensors, ensuring consistent output from batch to batch. At this point in the process, the chocolate mixture has reached a smooth, glossy, and richly aromatic state. It flows as a thick liquid, its flavors matured and balanced from hours of careful mixing, grinding, and aeration. The next phase transforms that liquid mass into a finished, stable form suitable for packaging and distribution. This involves cooling and crystallizing the cocoa butter within the mixture in a very specific way, a stage that requires precision and control over time, temperature, and movement. The goal here is to encourage the formation of the right type of crystal structure in the cocoa butter. Cocoa butter can solidify into several different crystalline forms, but only one of them results in a final product that has a smooth surface, sharp snap, resistance to melting in the hand, and a stable shelf life. To achieve this, the entire mass must be carefully tempered. Tempering is carried out in machines built for continuous flow and temperature control. These tempering units begin by first heating the mixture slightly above the melting point of all crystal forms, typically around 45 degrees Celsius. This ensures that any existing crystal structures are completely melted away. The liquid is then cooled gradually, usually to somewhere between 26 degrees Celsius and 28 degrees Celsius, depending on the specific type being produced. During this cooling, movement is maintained through stirring blades and flow channels, allowing the desired type of stable crystal to begin forming. Once enough of these seeds have developed, the mixture is gently reheated to a precise finishing temperature, usually just under 32 degrees Celsius. This final temperature is critical. It allows the seeded crystals to remain while eliminating the unstable forms that would cause bloom or textural issues later on. The flow, agitation, and temperature must be maintained within a very tight range. Modern tempering equipment uses inline sensors and feedback control loops to monitor these values in real time, ensuring the product is correctly tempered before it moves into the next station. From here, the tempered liquid is conveyed to the molding lines. These are high-speed, fully automated systems designed to pour precise volumes into molds of various sizes and shapes. The molds themselves are preheated slightly to prevent premature setting and ensure even flow. As the mixture is deposited into each cavity, vibratory tables shake the molds to remove any trapped air bubbles and ensure a perfectly even distribution. Once filled and vibrated, the molds are sent through long cooling tunnels. These enclosed, refrigerated belt systems gradually reduce the temperature in controlled stages, allowing the internal structure to set without cracking or warping. The airflow, tunnel speed, and humidity are all precisely calibrated to avoid moisture condensation on the surface, which could lead to dull or sticky finishes. Once cooled and fully solidified, the bars or shapes are released from the molds using a combination of mechanical pushes and short bursts of air. The finished items are then transferred onto conveyors that lead to the inspection zone. Here, vision systems scan each piece for defects, looking for uneven surfaces, cracks, color inconsistency, or any signs of bloom. Imperfect units are automatically ejected from the line for recycling. In many operations, these rejected items are remelted and retempered to be used again in the next batch. From this point, the finished product moves toward wrapping and packaging. The type of packaging depends on the product format, whether individual bars, boxed assortments, filled shapes, or bulk items for further processing. For single bars, wrapping lines are designed to handle high volumes per minute. Each bar is conveyed through a wrapping machine that cuts, folds, and heat seals the wrapper with high-speed precision. These machines are synchronized with the flow of the production line to prevent jamming, tearing, or misalignment. Packaging materials include metallized films, waxed paper, biodegradable foils, or composite laminates. These materials are selected based on the storage requirements of the product, the region's environmental regulations, and the shelf life goals. Many manufacturers also include oxygen scavengers or modified atmosphere sealing to enhance freshness, especially for filled products. After wrapping, individual bars or pieces are grouped into larger cartons or boxes by pick-and-place robotics. These machines identify product orientation, pick them up using suction or mechanical fingers, and place them into retail boxes, display trays, or bulk cases. The outer cartons are sealed, labeled, and pass through final quality control scanners that confirm weight, barcode accuracy, and expiration coding. Palletizing comes next. Stacked and secured cartons are placed onto shipping pallets according to loading patterns that maximize space efficiency and minimize stress on the bottom layers. Pallets are shrink-wrapped using rotating arms or heat tunnels, and then labeled with shipping codes, batch numbers, and destination data. The entire production record for each batch is digitally logged in the factory's quality control database. This includes source information for the raw ingredients, roasting and grinding parameters, conching durations, tempering temperatures, molding timestamps, and final inspection results. Should any issue arise downstream in distribution or retail, the system allows full traceability back to the moment each unit was created. Finished pallets are moved to climate-controlled storage zones. These warehouse areas are kept at stable temperatures, generally between 16 degrees Celsius and 20 degrees Celsius, to prevent melting, blooming, or flavor degradation. Humidity is also controlled, often under 60%, to protect the product and packaging integrity. Some products are stored under specific lighting conditions to prevent discoloration, particularly white and milk varieties that are more sensitive to UV exposure. Finally, shipments are released according to production schedules aligned with distribution needs. Orders are grouped by destination region, retailer, or distributor and loaded into trucks, shipping containers, or cargo planes. Temperature data loggers may be placed inside shipments to confirm that climate conditions remain within acceptable limits throughout transport. Though the product has now left the facility, its connection to the factory process is never lost. Retail complaints, test results, or customer feedback can all be traced back to the specific day, shift, and equipment used. Manufacturers regularly run shelf life simulations, flavor degradation tests, and mechanical stress analyses on packaged goods to validate the effectiveness of the process long after the final product leaves the line. Every stage, from raw bean to packaged bar, is designed not just for efficiency, but for repeatability and control. Factories producing chocolate operate like laboratories with strict protocols, while still honoring the craft behind each ingredient's transformation. This combination of technical discipline and sensory artistry is what makes industrial chocolate manufacturing one of the most exacting and fascinating operations in the global food industry. Once the finished chocolate leaves the factory, perfectly tempered, molded, cooled, and sealed in its final packaging, the industrial process doesn't come to a halt. A crucial final phase still unfolds, one that ensures the product not only reaches shelves in perfect condition, but also maintains its quality and integrity through transportation, storage, retail display, and eventual consumption. This extended phase is managed through sophisticated logistics, environmental monitoring, supply chain coordination, and continuous quality assurance practices. While this may seem like the back end of production, it is deeply integrated into how chocolate is made and maintained on a global scale. Immediately after production, the packaged chocolate is transferred into climate-controlled storage areas within the factory's distribution wing. These areas are tightly regulated to prevent degradation. The ideal temperature for storing finished chocolate is generally between 16 degrees Celsius and 20 degrees Celsius, with humidity kept below 60%. Above this humidity threshold, there is risk of sugar bloom, a white, dusty coating that forms when moisture causes sugar to dissolve and then recrystallize on the surface. Below this range, especially in dry climates, static electricity and brittleness can become issues, particularly for filled or aerated varieties. Storage racks are arranged to allow airflow between pallets. Each pallet is tagged with a unique identifier and scanned into the warehouse management system. This allows the system to track not only where each batch is physically stored, but also how long it's been in inventory, where it needs to go next, and whether it's awaiting any last-minute quality hold releases. Before a batch can ship, a final set of post-production tests is sometimes performed on a sample group. These tests may include accelerated shelf life simulations, where chocolate is exposed to varying environmental conditions in climate chambers to determine how it performs over time. Texture analyzers may test for brittleness or softening, while gas chromatography may be used to check whether volatile flavor compounds remain stable. Once cleared, shipments are scheduled for distribution. Whether headed to a supermarket distribution center, a specialty retailer, or international export, the chocolate must be loaded into transport systems that preserve the exacting conditions it was stored under. This can involve refrigerated or climate-controlled trailers, especially for higher-end varieties or filled products that are more vulnerable to heat. During warmer seasons, some companies delay shipments until nightfall or equip their pallets with insulation wraps to preserve temperature during brief exposure windows. Transport vehicles are often equipped with onboard temperature loggers. These small, battery-powered devices record environmental conditions every few minutes and are reviewed upon delivery to confirm that there were no unacceptable spikes in heat or humidity. If the data shows a breach, the receiving party may reject the shipment, even if the exterior packaging appears untouched. This level of accountability ensures that the integrity of the product is never assumed, but always confirmed. At the retailer level, chocolate continues to face environmental risks. Supermarkets and convenience stores may place chocolate in non-refrigerated aisles where exposure to lighting, fluctuating temperatures, and air conditioning vents can impact quality. To mitigate this, factory teams sometimes conduct in-store audits, either directly or through contracted merchandising specialists. These audits include checks on product placement, shelf temperature, rotation practices, and visible quality. Manufacturers also perform pull tests, where random samples are purchased directly from stores and sent back to internal labs for analysis. This helps determine if the product maintains its texture, snap, and flavor after weeks or months in the distribution system. These real-world results are fed back into the production process, helping engineers refine shelf life goals, tweak packaging barrier specifications, or adjust emulsifier ratios for better thermal resilience. Despite this rigorous system, the industrial process isn't rigid. Many manufacturers now build flexibility into their operations to support seasonal releases, new flavor experiments, and evolving consumer preferences. This includes small batch production lines within large factories that can produce limited runs of new recipes without interrupting mass-scale output. Even with these small lines, all the same steps: roasting, refining, conching, tempering, molding, wrapping are followed precisely, but in more agile formats. The long arc of chocolate production, from tropical farm to factory and beyond, is a story of transformation, precision, and protection. Each stage is critical, from developing flavor precursors during fermentation, to unlocking complexity through roasting, to achieving that final, glossy finish through proper tempering and cooling. It's not just about creating a product, it's about preserving it, tracking it, testing it, and delivering it across continents in exactly the state it was intended. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking, and an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the almond joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from coconut grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers. and the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package. In the massive production facilities where Reese's peanut butter cups are made, the process begins well before any chocolate is poured or any peanut butter is mixed. It starts with sourcing two critical ingredients: high-quality peanuts and specially formulated chocolate. The peanuts arrive at the plant in large, tightly sealed containers, having already undergone preliminary sorting at dedicated processing centers. However, the Reese's factory does not take any chances. Upon arrival, each shipment of peanuts is sampled and tested for aflatoxins, moisture content, and flavor quality. Only the best peanuts pass through to the next stage. The first critical transformation begins in the peanut roasting room, a cavernous area lined with continuous batch roasters. These machines look like giant horizontal drums that rotate slowly, while hot air circulates inside, ensuring each peanut is evenly toasted to bring out its natural oils and enhance flavor. Temperatures inside the roasters are tightly controlled, typically between 300 and 350 degrees Fahrenheit, and the roasting cycle can last anywhere from 10 to 30 minutes, depending on peanut size and desired roast level. Workers monitor color readings using optical sensors, making slight adjustments to the roast if necessary to achieve that signature Reese's flavor. Once roasted, the peanuts are transferred via conveyor belts to powerful cooling tunnels. Giant fans blow chilled, filtered air over the peanuts to halt the roasting process immediately, locking in the flavor profile. After cooling, the peanuts pass through a series of magnetic separators and vibrating screens to remove any foreign materials or remaining shell fragments, ensuring absolute purity. Next comes the grinding phase. The roasted peanuts are funneled into industrial grinders, massive machines equipped with heavy-duty steel plates that spin at high speeds. The first grind reduces the peanuts into a rough paste. Then a secondary, finer grind transforms the mixture into the silky, smooth peanut butter that will fill every cup. During grinding, small amounts of sugar, salt, and a plant-based emulsifier are added to stabilize the peanut butter and give it the slightly sweet, distinctly savory flavor that fans recognize instantly. The temperature is carefully managed during this phase, usually kept between 120 and 140 degrees Fahrenheit to ensure the oils remain stable and the texture remains creamy but not runny. The freshly made peanut butter is then pumped into enormous stainless steel holding tanks, where it is kept warm and agitated gently to maintain a consistent texture. These tanks are connected by sanitary piping to the production lines, allowing for seamless and hygienic movement of the peanut butter when it's time to fill the cups. Meanwhile, the chocolate preparation is already underway in a different section of the factory. Reese's uses a specially formulated milk chocolate blend that balances sweetness, cocoa flavor, and a creamy melt-in-the-mouth texture. Bulk chocolate arrives in the form of large solid blocks or liquid tanker shipments, depending on the factory's setup. If solid, the chocolate is first broken down in massive pre-melters, slowly heating it to around 110 degrees Fahrenheit to achieve a uniform, molten state. Once liquefied, the chocolate is pumped into tempering machines, sophisticated systems that cool and reheat the chocolate in a precise curve to stabilize the cocoa butter crystals. This tempering process is critical. It gives the finished cups their glossy appearance, firm snap, and excellent shelf stability. Now, with both chocolate and peanut butter ready, the cup assembly line begins. First, paper cup molds are automatically dispensed onto a continuously moving conveyor belt. High-speed chocolate depositor machines then squirt a carefully measured amount of molten chocolate into each paper cup, forming the base layer. The conveyor belt vibrates gently to help the chocolate settle evenly across the bottom and slightly up the sides of each mold. Immediately after this, the conveyor moves the cups through a cooling tunnel, where chilled air at around 50 degrees Fahrenheit partially solidifies the base chocolate layer. This quick cooling ensures that when the peanut butter is deposited, it won't sink all the way to the bottom of the cup, maintaining the ideal layered structure. Next, the creamy peanut butter is deposited into the center of each chocolate base using precision nozzles. The amount of peanut butter is meticulously controlled by programmable pumps, ensuring every Reese's cup has the same perfect peanut to chocolate ratio. Interestingly, the peanut butter filling itself is slightly cooler than the chocolate, typically around 80 to 90 degrees Fahrenheit, which helps it stay firm during the next stages of production. After the peanut butter is deposited, a second layer of molten chocolate is dispensed over the top, sealing in the peanut butter and forming the upper shell of the candy. Again, careful vibration of the conveyor ensures a smooth, even surface. At this point, visual inspection systems using high-speed cameras and AI algorithms scan the cups for consistency, checking fill levels, alignment, and any surface imperfections. Defective cups are automatically rejected from the line. The filled cups then pass through an extended cooling tunnel where they spend several minutes gradually chilling back down to around 45 degrees Fahrenheit. This staged cooling prevents the chocolate from blooming, a condition where cocoa butter rises to the surface and creates an unsightly white film. Instead, the cooling process locks in that deep, shiny chocolate sheen. Once fully cooled, the cups are ready for packaging. Automated robotic arms gently lift rows of finished Reese's cups and place them into pre-formed trays or directly onto flow wrapping machines. Each candy is enveloped in a thin, protective layer of branded orange packaging film. Heat sealers quickly fuse the edges of the wrapper shut, trapping a pocket of nitrogen gas inside. This inert atmosphere helps prevent oxidation, preserving freshness and flavor for extended shelf life. The wrapped candies are then grouped into multi-packs by high-speed cartoning machines, which fold and seal cardboard boxes around designated numbers of cups, whether it's a standard 2-pack, a king-size 4-pack, or a family-size bag of miniatures. These boxes are coded with manufacturing dates, lot numbers, and other traceability data before being stacked neatly onto pallets. Before the pallets leave the factory, a final quality control check is performed. Random packages are pulled from the line and subjected to a battery of tests, including weight checks, taste tests, visual inspections, and even X-ray analysis to ensure there are no contaminants or structural flaws inside the candies. Only when these samples pass inspection are the pallets shrink-wrapped and labeled for distribution. From there, the Reese's Cups embark on their journey through a highly coordinated supply chain. Pallets are loaded onto refrigerated trucks, kept at cool but not freezing temperatures to prevent the chocolate from melting or degrading. Distribution centers across the country receive the shipments, from which they are sent to grocery stores, convenience shops, vending machine suppliers, and even directly to online retailers. What's fascinating about the Reese's production process is how every detail, temperature, timing, movement, is optimized for both speed and quality. The factories are largely automated, with programmable logic controllers and centralized computer systems coordinating every phase, minimizing human error and maximizing consistency. Maintenance crews monitor the machinery continuously, ready to intervene if even the slightest deviation occurs. Yet, despite the heavy automation, a skilled team of chocolatiers, food scientists, and process engineers oversee operations daily, ensuring that the soul of the Reese's cup, the perfect balance of creamy peanut butter and silky milk chocolate, is never compromised. In recent years, new technologies have further enhanced production. Advanced predictive maintenance uses AI algorithms to detect early signs of equipment wear, preventing costly downtime. Robotic packaging systems have become faster and more flexible, adapting to different product formats with minimal reprogramming. Even energy efficiency has improved dramatically, with modern factories recapturing waste heat from the roasting and tempering processes to reduce overall power consumption. The result of all this effort is what you hold in your hand, a Reese's peanut butter cup with the same incredible taste that has delighted generations. From careful peanut selection to intricate chocolate tempering, from the first squirt of chocolate to the final seal of the wrapper, every step is a marvel of precision, engineering, and culinary artistry, ensuring that each bite delivers the unmistakable Reese's experience, time after time. The making of Hershey's milk chocolate begins long before any bars are molded or wrapped. It starts with sourcing one of the world's most essential commodities, cacao beans. Hershey's purchases massive quantities of cacao from regions like West Africa, Central and South America, and parts of Southeast Asia. Upon arrival at Hershey's specialized facilities, the cacao beans undergo strict quality control protocols. Sampling machines pull randomized beans from each shipment, checking for mold, contamination, fermentation quality, and flavor profiles. Only beans that meet Hershey's high standards proceed to production. The first major operation is cleaning. Beans travel through a series of shaking screens, magnetic separators, and powerful air jets that remove debris like sticks, stones, and dust. Once cleaned, the beans are routed to the roasting department. Here, colossal stainless steel drum roasters, each capable of handling thousands of pounds per batch, bring the beans up to roasting temperatures of around 250 to 300 degrees Fahrenheit. This roasting phase is crucial. It not only develops the rich cocoa flavors, but also loosens the shell from the nib, the part of the bean that will become chocolate. After roasting, the beans pass through cracking and winnowing machines. Heavy rollers crack the beans open, and powerful airflows then separate the lighter, papery shells from the heavier cocoa nibs. The nibs are collected and sent immediately into the refining phase. The shells, interestingly, don't go to waste. Many are repurposed as agricultural mulch or used in animal feed. The next transformation happens in the grinding rooms. Industrial grinders crush the nibs into a thick, gritty paste known as chocolate liquor. Despite its name, it contains no alcohol. Giant stone mills or modern ball mills spin tirelessly, reducing particle sizes to less than 100 microns. This grinding process releases the cocoa butter within the nibs, turning the dry nibs into a fluid, rich mass. At this stage, the chocolate liquor is either stored or immediately processed depending on the specific recipe being produced. For Hershey's signature milk chocolate, chocolate liquor alone is not enough. It must be blended with several other ingredients: sugar, milk, and cocoa butter, among others. Hershey's famously uses fresh condensed milk rather than powdered milk, a technique that imparts its distinctive flavor. Tankers bring in condensed milk that has already been pasteurized and quality tested for microbial safety. The milk is combined with sugar in large stainless steel kettles and cooked to form what is known as a milk crumb, a dry, sweet, caramelized powder that becomes the base for Hershey's milk chocolate. The milk crumb, chocolate liquor, and additional cocoa butter are blended together in massive mixers that resemble horizontal cement mixers but are built for food-grade standards. In these tumbling vessels, the blend of ingredients becomes a coarse chocolate dough. This dough is then fed through refining rollers, 5 or 6 massive, polished steel rollers stacked horizontally. As the dough passes through each successive roller gap, it is compressed and sheared finer and finer, reducing the sugar and cocoa particles to just the right microscopic size to ensure a smooth texture. At this point, the chocolate still lacks the silky consistency and full flavor that people expect. That's where one of the most crucial steps in chocolate making enters: conching. Hershey's uses giant conching machines, massive, heavy-duty mixers with granite rollers that agitate, aerate, and warm the chocolate dough for hours. Traditional conching could take up to 72 hours, but with modern methods and specialized Hershey's technology, the time has been optimized without sacrificing quality. During conching, volatile acids and bitter flavors evaporate away, while cocoa and milk flavors mellow and deepen. At the same time, the continuous mixing further reduces any remaining coarse particles and disperses the cocoa butter thoroughly throughout the mass. Temperature control during conching is critical. The chocolate must stay within an exact range, typically between 130 to 180 degrees Fahrenheit, depending on the desired flavor development. Ventilation hoods draw off unwanted volatiles, and sensors embedded throughout the conches constantly report data back to automated control systems, adjusting speed and temperature as needed. Following conching, the chocolate moves into the tempering phase. Tempering is an art and science all its own. Chocolate is carefully cooled and reheated through specific temperature curves to create stable cocoa butter crystals. This gives finished chocolate its snap, gloss, and resistance to melting at room temperature. Hershey's uses continuous tempering machines, which can process thousands of pounds per hour. These machines use a series of heated and cooled zones to guide the chocolate through its crystal formation journey with pinpoint accuracy. Improper tempering would result in chocolate that's dull, crumbly, or prone to blooming, a white discoloration, so this step must be executed flawlessly. Once tempered, the liquid chocolate is transported through heated pipes to the molding stations. There, automated depositors squirt precise amounts of chocolate into endless arrays of molds, some shaped for classic Hershey's bars, others for miniature versions or seasonal specialties. The molds vibrate rapidly on oscillating tables to eliminate any air bubbles and ensure an even surface. The molds then enter a long cooling tunnel, a carefully calibrated environment where the chocolate solidifies slowly and evenly. Inside the tunnel, the temperature drops gradually from around 70 degrees Fahrenheit to about 50 degrees, preventing thermal shock and ensuring that the chocolate sets with a fine, smooth crystal structure. After cooling, the solid chocolate is demolded. High-speed mechanical arms flip and flex the molds, gently releasing the perfectly formed bars onto conveyor belts. At this stage, visual inspection systems equipped with high-speed cameras and AI check every piece for uniformity, detecting even minor surface defects or molding errors. Imperfect chocolates are removed from the line for recycling back into the production process. The next step is packaging. For Hershey's bars, the chocolate rides conveyors into flow wrapping machines. Each bar is enveloped in a tight sleeve of foil and then an outer branded paper wrapper. Modern flow wrappers work at astonishing speeds, often wrapping hundreds of bars per minute with perfect precision. The wrapped bars are coded with expiration dates, batch numbers, and tracking information to ensure full traceability from production through to sale. Once wrapped, the bars are collated into cartons or retail trays by robotic packers, which arrange them neatly in boxes that are then sealed, labeled, and stacked onto pallets. Before shipment, a random sample from every production batch undergoes additional quality assurance tests, including break tests, melt tests, taste panels, and microbial analysis. Only after passing all these checks are the pallets released for distribution. The finished Hershey's milk chocolate bars then enter the logistics phase, moving through regional distribution centers that coordinate delivery to supermarkets, convenience stores, cinemas, and countless other retailers around the world. Throughout the distribution chain, temperature control remains critical. Warehouses and trucks are climate controlled to prevent the bars from experiencing temperature swings that could cause chocolate bloom or textural changes. Throughout the entire factory process, Hershey's leverages advanced automation, continuous monitoring, and decades of chocolate-making expertise to ensure that every bar tastes as iconic and consistent as the last. The level of control is extraordinary. Chocolate viscosity, particle size distribution, moisture levels, and flavor profiles are measured and adjusted in real time using sophisticated inline sensors and laboratory tests. In recent years, Hershey's has also invested heavily in sustainability, working directly with cocoa farmers through its Cocoa for Good program to promote ethical sourcing, better farming practices, and environmental stewardship. This commitment ensures not just the continued availability of high-quality cacao, but also a better future for the communities that produce it. The journey of a Kit Kat begins with two major components: the chocolate coating and the crisp wafer core. Both are manufactured separately and in parallel streams before being married together into the unmistakable Kit Kat form. Each ingredient, each layer, and each step is engineered with astonishing precision to create the perfect snap, crunch, and creamy finish that Kit Kat is famous for. The process starts with the preparation of the chocolate. Kit Kat's signature coating is slightly different from pure chocolate. It is technically a compound chocolate, specially formulated to give a smooth melt and quick setting properties ideal for enrobing wafers. At factories like Nestlé's York facility in the UK or similar plants worldwide, bulk cocoa liquor, cocoa butter, sugar, and milk solids are combined. The cocoa beans that form the basis of the liquor are sourced from sustainable suppliers, cleaned, roasted, and ground into fine paste months before production even begins. To prepare the chocolate coating, the cocoa liquor is blended with sugar and powdered milk in enormous stainless steel mixers. This mixture is then refined through a series of precision-calibrated rollers, reducing the particle size to around 20 microns, finer than the human tongue can detect. The refining phase is essential to create the smooth mouthfeel Kit Kat lovers expect. Following refinement, the chocolate mass moves into conching machines, where it is slowly mixed, aerated, and heated. This removes any bitter flavors and unwanted acidity, while promoting the development of a creamy, caramel-like flavor that defines Kit Kat's chocolate. Temperature control during conching is rigorously maintained at around 135 to 180 degrees Fahrenheit, depending on the recipe. Once the chocolate reaches the right flavor and viscosity, it is moved into tempering units, where it's carefully cooled and reheated to produce stable cocoa butter crystals. Proper tempering ensures that the finished chocolate will have a shiny appearance, a satisfying snap, and resistance to blooming. Meanwhile, in another section of the factory, the production of the wafer sheets is underway. Wafer batter, made from a simple mixture of wheat flour, sugar, vegetable oil, leavening agents, and water, is mixed in giant, computer-controlled vats. The batter is pumped through piping systems directly to high-speed wafer baking ovens, each stretching tens of meters in length. These wafer ovens consist of two continuously moving steel belts that sandwich the batter and pass through a baking tunnel. As the belts travel, radiant heat, conduction, and convection work together to bake the batter into ultra-thin, crisp wafer sheets. Each sheet emerges from the oven perfectly cooked, around 2 to 3 millimeters thick, with a delicate, light texture and a uniform golden brown color. After baking, the wafer sheets are rapidly cooled using forced chilled air to prevent moisture absorption. They are stacked and transported via conveyor belts to the cream spreading stations. Here, a thin layer of specially formulated filling, a mixture typically based on ground wafer crumbs, vegetable fats, sugar, and milk solids, is evenly spread across the wafers. The filling not only enhances the flavor, but also acts as a structural adhesive, bonding the multiple wafer layers together. Usually, 3 or 4 wafer sheets are stacked, with cream filling between each layer. These multi-layered blocks are then pressed under controlled pressure to ensure perfect bonding without cracking or crushing the delicate wafers. After resting for stabilization, the wafer blocks are transferred to high-speed cutting machines. The cutting process is a masterpiece of mechanical precision. Using laser guides and ultrasonic blades, the blocks are sliced first longitudinally, then crosswise into the familiar slim Kit Kat finger dimensions. Every cut must be perfect. Any deformation could later disrupt the enrobing process or spoil the iconic snap experience. Once cut, the wafer fingers are ready for enrobing. Conveyors carry them through a chocolate waterfall inside the enrobing machines. A curtain of tempered Kit Kat chocolate cascades over the wafers, completely coating them on all sides. Excess chocolate is blown off the bottom with controlled air jets, creating the thin chocolate layer underneath that gives Kit Kat its balanced chocolate to wafer ratio. Directly after enrobing, the fingers pass through a vibrating section of the conveyor to settle the chocolate coating and eliminate air bubbles. They then enter a series of cooling tunnels where cold, dry air, typically kept between 40 and 50 degrees Fahrenheit, slowly solidifies the chocolate coating without causing condensation, which would ruin the texture. At this point, the individual fingers are grouped together. Kit Kat is traditionally made with 4 fingers to a bar, although mini versions, single fingers, and chunkier variants are also produced. Robotic arms align and group the fingers with exact spacing between them before feeding them into wrapping machines. Kit Kat's iconic red and white wrapper is a masterpiece of branding and practical design. Wrapping is done using ultra-fast flow wrappers that synchronize perfectly with the grouping conveyors. Each set of fingers is enveloped in foil or a plastic laminate film, which protects against moisture and oxygen while maintaining the crunch of the wafer and the smoothness of the chocolate. The wrapping machines heat seal the edges at high speed, and rollers gently press and fold the sealed packs for that crisp, tight package finish Kit Kat is known for. As the wrapped bars move down the line, high-speed scanners and cameras inspect each package for correct seal integrity, label placement, and print clarity. Imperfections are detected in milliseconds, and defective packs are automatically ejected into collection bins for recycling. Once the Kit Kats are individually wrapped, the next stage is boxing and palletizing. Robotic case packers arrange the wrapped bars into boxes or display cartons, which are then sealed with automatic tapers and labeled with tracking information. Each box is carefully weighed and scanned to ensure it matches target specifications before being stacked onto pallets by robotic arms or palletizing machines. Throughout the entire production process, rigorous quality control is applied at every major step. Samples of chocolate, wafer batter, finished wafers, and completed bars are pulled at regular intervals for lab analysis. These tests include moisture content checks, microbiological safety testing, taste panels, and break strength tests to ensure the classic crisp break of a Kit Kat remains perfect batch after batch. In addition to inline testing, larger batch samples are subjected to accelerated aging studies to simulate how the product will perform over its shelf life. Sensory evaluation booths, staffed by trained taste testers, ensure that every batch maintains the exact flavor, aroma, texture, and mouthfeel that consumers expect. Once the Kit Kats are boxed and palletized, they are shipped out from climate-controlled distribution centers. Transport conditions are carefully managed to prevent temperature fluctuations that could cause chocolate bloom or wafer softening. Many shipments are refrigerated during summer months or in hotter climates to guarantee the product arrives in prime condition. Kit Kat's industrial production is a brilliant choreography of automation, sensory science, and quality management. Despite the high level of automation, human oversight remains crucial. Line operators monitor critical control points, adjust machine settings, respond to alarms, and carry out maintenance to keep the lines running smoothly, often 24 hours a day, 7 days a week. Recent advancements have further refined the process. State-of-the-art production lines now incorporate AI-driven predictive maintenance, allowing engineers to anticipate mechanical failures before they happen. Machine learning algorithms also optimize ingredient mixing, cooking times, and cooling profiles, subtly adjusting for real-time variables like humidity, ingredient lot variation, or slight temperature shifts in the facility. KitKat's commitment to sustainability is woven into production as well. Modern factories are equipped with energy recovery systems that reuse heat from the ovens and chillers. Water used in cooling and cleaning processes is recycled wherever possible. Additionally, KitKat's cocoa is 100% sourced through programs like Rainforest Alliance certified farms, ensuring ethical and environmentally responsible cocoa farming practices. Each KitKat bar that makes it into a consumer's hands is the end product of thousands of micro decisions and perfectly tuned processes: baking, layering, cutting, coating, cooling, wrapping, all executed with a level of precision that would make a Swiss watchmaker proud. The crisp snap of the break, the lightness of the wafer, the creamy melt of the chocolate. Every detail is the result of decades of research, refinement, and relentless pursuit of chocolate and wafer perfection. It all begins with the peanuts. While it might seem obvious that a peanut butter cup would start with peanuts, what's not widely known is just how much control and specificity Hershey applies to this ingredient before it ever reaches the cup itself. Reese's production lines require massive quantities of peanuts, hundreds of tons per week across facilities, and not just any peanut will do. The factory demands high oleic runner peanuts, most commonly sourced from farms in Georgia, Alabama, and Texas. These peanuts are preferred for their uniform kernel size, mild flavor, and high oil content, which delivers a creamier peanut butter base. Once harvested, peanuts are sent to dedicated shelling and blanching facilities, where they are cleaned, sorted, and skinned. The outer red skins are removed through dry abrasion, and the kernels are visually and electronically inspected to eliminate any with defects, mold, or foreign materials. Only the highest grade peanuts, typically designated as US Fancy or US Extra Large, are accepted for Reese's production. These peanuts are then loaded into food-grade hoppers and shipped in sealed bulk containers to the peanut butter manufacturing lines at Hershey's centralized processing plants. Upon arrival at the factory, the peanuts are stored in stainless steel silos within a climate-controlled environment to prevent spoilage. Prior to use, the peanuts are metered into roasting drums. Roasting is a critical step not just for flavor, but for aroma development and moisture reduction. High-capacity rotary roasters or continuous conveyor-style roasters are used, depending on the factory's line design. Peanuts are typically roasted at temperatures between 320 degrees Fahrenheit and 360 degrees Fahrenheit for 30 to 45 minutes. The exact temperature curve is adjusted based on peanut moisture and oil content, which is sampled batch by batch in the factory's lab using gas chromatography and moisture analyzers. The roasters are equipped with air impingement systems and inline sensors to monitor internal temperature, color, and roast development in real time. At various intervals, small test samples are pulled using auto draws for taste panel review. Roast level has to be absolutely consistent, as this is the foundation for the signature Reese's peanut butter flavor. Over-roasted peanuts will produce a burnt or overly bitter taste, while under-roasting leaves the flavor bland and oily. Once roasted, peanuts are cooled using high-powered air chillers to prevent overcooking and to stabilize the oils. They are then conveyed into degermers and mechanical splitters, where they are cracked open and the hearts, the hard inner core of the peanut, are removed. These hearts, while technically edible, can impart a bitter or chalky aftertaste, so they are separated out and typically used in livestock feed or secondary food processing streams. Now comes the grinding phase. The roasted and cooled peanuts are fed into large, high-shear grinders, industrial versions of what's used in commercial peanut butter production. These grinders operate at extremely high RPMs and are often configured in a two-stage system: a coarse grind followed by a fine grind. In the coarse phase, the peanuts are broken down into a grainy paste, preserving small particulates that contribute to the slightly gritty texture of Reese's peanut butter. This paste is then piped into a second mill, where it's refined to a smooth, uniform consistency. The peanut paste is blended in stainless steel mixing tanks equipped with variable speed paddles and heated jackets. At this stage, a proprietary mix of additional ingredients is incorporated. These include salt, sugar, a small amount of fully hydrogenated vegetable oil, and a dry milk derivative. The sugar used is finely milled and sieved to a consistent particle size, ensuring it disperses evenly throughout the mix without recrystallizing. Emulsifiers such as mono and diglycerides are added in microdoses, enabling the fat and protein phases to remain homogeneous over time. What makes Reese's filling unique, and one of the factory's guarded secrets, is its texture. It isn't traditional creamy peanut butter. It's dry and crumbly, almost fudge-like, but melts smoothly on the tongue. This is achieved by very specific moisture and fat content targets. The factory carefully controls the fat ratio in the peanut blend using inline nuclear magnetic resonance sensors, which measure fat levels without destroying samples. The ideal balance results in a pliable, moldable filling that holds its shape during chocolate enrobing but softens under bite pressure. Once blended, the peanut butter filling is pumped into chilled hoppers and held at precise temperature, typically between 60 degrees Fahrenheit and 70 degrees Fahrenheit, so it can be extruded or deposited with exact weight and shape control. Temperature consistency is crucial here. Too warm, and the filling becomes too soft and spreads when deposited. Too cold, and it hardens and resists clean shaping, risking damage to the chocolate cup. The final stage in this first segment is the formation of the peanut butter centers. On a separate production line, the cooled peanut filling is portioned using servo-driven pistons or extrusion rollers, depending on the cup format being produced. These machines deposit small, perfectly measured mounds of filling onto a chilled conveyor. In larger cups, the filling is puck-shaped. In minis, it's closer to a small dome. Each peanut butter deposit is then transferred into a temporary holding tunnel, essentially a refrigeration corridor, where the shaped fillings are stabilized prior to the chocolate enrobing phase. Here, humidity and temperature are carefully balanced to avoid condensation or fat bloom when chocolate is later applied. At this point, the peanut butter centers are firm, uniform in size and shape, and fully ready for the next critical phase of the process, chocolate molding. With the peanut butter centers now precisely formed, cooled, and stabilized, the next critical phase in the industrial production of Reese's peanut butter cups begins: chocolate shell creation and cup assembly. This portion of the process is all about precision, timing, and the seamless integration of multiple complex systems to produce a product that's visually perfect and texturally balanced. It's here that the familiar cup shape begins to take form, and where Hershey's decades of manufacturing expertise are on full display. The chocolate used in Reese's products is developed in-house and differs slightly from that used in a Hershey's milk chocolate bar. While it still contains cocoa solids, cocoa butter, milk solids, sugar, and lecithin, it has been tailored specifically to pair with the salty sweet peanut butter filling. The chocolate is slightly softer in melt, less bitter than dark chocolate, and has a fat and sugar profile that ensures it doesn't overpower the filling. It's formulated to be both moldable and stable, under typical shelf conditions, even in warmer climates. The chocolate arrives at the cup production line in a liquid state, held in large tempering tanks kept at a precise temperature, usually around 30 to 32 degrees Celsius for milk chocolate. Tempering is an essential part of chocolate manufacturing and involves heating the chocolate to fully melt its cocoa butter crystals, cooling it to initiate the formation of stable type 5 crystals, then gently reheating it to bring it to working temperature. This process ensures that once the chocolate is set, it has a glossy finish, resists bloom, and has a clean snap when broken. The first step in forming the Reese's cup is lining the signature brown paper cup mold with chocolate. The production line is fed with pre-formed paper cups stored in large reels or stacked columns that are automatically dispensed onto a high-speed conveyor. These paper cups are food-grade, waxed, or coated with a thin moisture barrier and shaped precisely to hold their structure during and after chocolate deposition. Once the paper cups are set in place on the moving line, a chocolate depositor head releases a measured dose of tempered chocolate into each one. This is known as the bottoming phase. The amount of chocolate is critical, not only for structure, but also for controlling the ratio of chocolate to filling. After deposition, the cups pass over a vibration table. This stage is crucial for evenly spreading the chocolate along the bottom and slightly up the sides of the paper cup. The vibration table uses rapid, controlled pulses to remove air bubbles and to ensure a uniform shell that won't crack or collapse during filling. Immediately following the bottoming step, the peanut butter centers are dropped into the liquid chocolate. These centers have been transferred from the refrigerated holding tunnel to the enrobing line and are picked and placed with robotic arms or pneumatic suction systems that gently lower each piece into its corresponding chocolate-lined cup. The timing of this placement is perfectly synchronized so that the peanut butter slightly sinks into the chocolate but doesn't hit the bottom, allowing a chocolate base to remain intact beneath the filling. As the peanut butter sits in the base, a second dose of chocolate is deposited on top. This is referred to as the capping phase. The capping head delivers another precise amount of tempered chocolate to completely enrobe the peanut butter core. This top layer seals the filling, ensuring the product is fully enclosed and protected from oxygen, moisture, and contamination. The final thickness of the cap is carefully calibrated so the chocolate shell is strong enough to hold shape, but still soft enough to bite through easily without excessive crumbling. The assembled cups, now complete with base, filling, and cap, are conveyed into a long, multi-zone cooling tunnel. These tunnels are often 20 to 30 meters in length and feature graduated temperature zones, starting at around 16 degrees Celsius and dropping to 8 to 10 degrees Celsius toward the end. The slow, controlled cooling is essential to prevent condensation or stress fractures in the chocolate. Too rapid a chill can cause bloom or cracking, while uneven cooling can result in misshapen edges or textural inconsistency. Inside the cooling tunnel, conditioned air circulates in laminar flow patterns, ensuring that every cup is exposed to identical cooling conditions. The duration of the tunnel cycle is calibrated to match line speed and product size. Larger Reese's big cups may require longer chill times compared to the classic or miniature versions. At the tunnel exit, the cups are inspected by automated vision systems that detect anomalies like off-center fillings, insufficient chocolate coverage, or edge deformation. Any defective cups are automatically diverted from the line for reprocessing. The cups that pass inspection are ready for packaging. But before that happens, there's one last critical test: weight and sealing verification. Inline check weighers use load cells to weigh each cup or group of cups to ensure they fall within designated tolerances. Simultaneously, barcode scanners and optical sensors check that each product is aligned and properly seated in its paper cup. The final stage before wrapping is an air dusting system that removes chocolate crumbs, static particles, or paper fragments from the surface to ensure a clean, polished presentation in the final package. Packaging of Reese's cups is a high-speed operation. Cups are grouped automatically into configurations appropriate for each product format: singles, twin packs, snack-size multi-packs, or seasonal variations. Each group is loaded into a continuous film wrapping machine, which pulls branded plastic film from a roll, wraps it around the cups, seals it with a heated crimper, and cuts it into individual packages. The film is pre-printed with product information, UPC codes, and freshness dates that were applied earlier by industrial flexographic printers. Once wrapped, the products pass through another metal detector or X-ray system to detect any foreign contamination that may have occurred during packaging, a standard in modern food manufacturing. Any anomaly results in immediate ejection and shutdown of the machine until the issue is resolved. The acceptable product continues to cartoning lines, where it is packed into retail-ready boxes, display trays, or bulk shipping cases depending on the destination. Finished product cartons are coded, palletized by robotic stackers, and shrink-wrapped for transport. Each pallet is labeled with a unique tracking number that links it to its production batch, shift number, ingredient lot codes, and quality control logs. This traceability allows for quick response in case of any issues in the supply chain. Every Reese's Peanut Butter Cup batch is subject to a comprehensive quality assurance protocol from start to finish. While visual inspection, weight checking, and foreign material detection handle surface-level defects, deeper analytical testing is performed regularly throughout production. Factory labs adjacent to the production floor run hourly tests on product samples pulled from the line. These tests measure water activity, pH levels in the peanut filling, chocolate temper index, fat content, and emulsifier concentration. Advanced equipment like near-infrared spectrometers and gas chromatographs are used to validate these metrics with precision. In addition to instrument-based testing, trained sensory panels perform blind evaluations of finished product samples. These panels, often composed of factory employees specially trained in flavor and texture recognition, assess everything from peanut aroma intensity to shell firmness, sugar balance, and mouthfeel contrast between chocolate and filling. Feedback from these panels is compared to golden standard benchmarks. Reference Reese's cups produced under ideal conditions that are stored in temperature and humidity-controlled archives. These control cups are regularly reviewed to ensure no drift in product quality over time. Allergen control is one of the most sophisticated systems running silently beneath the surface of Reese's production. Since peanuts and dairy are both major allergens, Hershey facilities that manufacture Reese's operate under strict protocols to prevent cross-contamination. Separate ingredient receiving docks, isolated storage silos, color-coded tool systems, and dedicated air handling zones are used to segregate peanut-related materials from other production lines within the same facility. Sanitation crews follow clean-in-place procedures using food-safe alkaline and acid-based cleaners to remove all traces of allergens between product changeovers. Swab testing for peanut protein residue is conducted on all contact surfaces before production resumes. Hershey also enforces supplier controls. All incoming peanut shipments are tested for aflatoxins, a class of toxic compounds produced by certain molds that can occur in improperly stored peanuts. Only peanuts that pass stringent safety thresholds are accepted, and each delivery is logged and tracked using batch codes that link to the final product's traceability system. This digital record keeping allows Hershey to track every ingredient back to its source farm and forward through every unit sold. But Reese's isn't just a singular product anymore. Over the years, the brand has expanded into dozens of variations: white chocolate cups, dark chocolate, big cups, miniatures, stuffed versions with pretzels, potato chips, Reese's Pieces, or caramel. Each variant requires its own unique processing conditions and introduces new complexity to the factory system. Let's take the white chocolate Reese's as an example. This variation uses a cocoa butter-based confectionery coating rather than traditional milk chocolate. It must be handled in separate melters and tempering systems due to its sensitivity to high heat and faster tendency to bloom. White chocolate also requires precise control of ambient light and humidity during production and packaging, as it is more susceptible to visual imperfections. On the line, switching from standard milk chocolate to white chocolate triggers a full line cleaning and recalibration of depositor and cooler settings. Flavor variants with inclusions, like Reese's with Reese's Pieces inside, add another layer of complexity. In these formats, the peanut butter filling is first blended with the inclusion, pieces, chips, or even candy bits, using slow-speed paddle mixers to avoid crushing or melting the added components. These inclusions alter the viscosity and extrusion behavior of the filling, requiring depositor nozzles to be widened and dosing pumps to be recalibrated for accurate weight control. Additionally, because candy-coated pieces can crack or leak color when exposed to oil migration from the peanut butter, the storage conditions of these fillings must be tightly managed to preserve structural integrity during molding. Even packaging formats are adapted. Big cups, which contain more filling and sometimes additional elements, require thicker paper cups and slightly wider flow wrapping machines to handle the larger size. Seasonal versions, like pumpkin-shaped Reese's for Halloween or tree-shaped cups for Christmas, require completely new mold tooling, reshaped paper cups, and different wrapping film dimensions. These seasonal SKUs are often produced in limited time production runs scheduled between mainline batches, with precise coordination between departments to minimize downtime and clean out inefficiencies. To manage this growing complexity, Hershey's manufacturing ecosystem is deeply integrated with real-time data and automation. Programmable logic controllers govern every stage of production, from peanut grinding to chocolate capping. These controllers constantly adjust conveyor speeds, depositor volumes, oven temperatures, and cooling rates to match product specifications in real time. Sensors along the line feed back information on humidity, belt tension, machine vibration, and material flow. If any parameter drifts beyond the preset tolerance window, an alert is triggered immediately and logged by the manufacturing execution system. The MES serves as the brain of the operation. It logs every batch, shift, operator, ingredient lot, and test result. It manages production schedules based on demand forecasting from Hershey's enterprise planning systems, and it ensures the right packaging, ingredients, and machines are prepared for the next product variation before the current one is even complete. The MES also interfaces with digital traceability systems, allowing Hershey to execute complete recalls if necessary, though this is extremely rare due to the redundant safety nets in place. To support sustainability goals, the factory also measures key environmental metrics. Energy usage from roasting, tempering, and cooling operations is tracked and optimized. Waste heat from roasters is sometimes redirected to preheat water for sanitation systems. Chocolate scrap from edge trimmings and overflows is collected and reworked in designated reclaim tanks. Even the cardboard used for cartons and paper used for wrapping is sourced from certified sustainable forestry programs. Water used in cooling tunnels is recirculated through industrial-grade filtration systems and UV sterilization loops, allowing for multiple reuse cycles before any disposal. Factory roofs are often equipped with solar panels, contributing to the site's renewable energy footprint. These sustainability measures not only support Hershey's corporate goals, they also help reduce operating costs and ensure compliance with international environmental standards, especially for exports to markets with strict eco-regulations. Finally, at the distribution level, finished pallets of Reese's are scanned, shrink-wrapped, and entered into a dynamic warehousing system. Pallet storage is optimized by weight, sell-by date, and destination zone. Reese's products are shipped in refrigerated trucks when needed, although standard varieties are stable at room temperature due to their low water activity and solid fat matrix. Shipments are tracked via GPS and load sensors to ensure they remain within safe handling conditions throughout transit. So when you open a Reese's peanut butter cup and experience the snap of chocolate, the softness of the peanut filling, and the perfectly even texture from edge to edge, what you're actually tasting is the output of a meticulously engineered, continuously monitored, and relentlessly optimized factory system. Behind every wrapper is a chain of roasting drums, tempering tanks, vibration tables, chilled tunnels, microlab samplers, PLCs, conveyors, AI sensors, and hundreds of trained hands working in quiet unison to make every bite familiar, reliable, and timeless. As Reese's peanut butter cups leave the controlled environment of production and are loaded onto outbound trucks, the story doesn't end with the last machine seal or pallet scan. In fact, one of the most underappreciated aspects of the manufacturing system lies in how Reese's maintains product integrity far beyond the factory walls. The journey from factory to store shelf, and ultimately to the consumer's hand, is an extension of the manufacturing process itself. For a product like Reese's, where texture, flavor, and structure are so carefully engineered, maintaining those qualities through shipping, storage, and retail presentation is non-negotiable. Temperature control plays a key role in this extended quality assurance chain. While Reese's peanut butter cups are classified as shelf-stable and do not require refrigeration, they are extremely sensitive to heat and humidity. Elevated temperatures can cause the chocolate to melt or bloom, a condition where cocoa butter rises to the surface and creates a whitish-grey coating. Though harmless, bloom gives the appearance of staleness or spoilage and is unacceptable in any retail-facing product. To prevent this, shipping containers and trucks are monitored using digital temperature loggers and GPS trackers. These devices not only ensure compliance with storage requirements, but also provide real-time alerts if conditions fall outside predefined thresholds. Warehousing and retail logistics are optimized with similar care. Distribution centers receiving Reese's shipments are instructed to rotate inventory on a strict first-in, first-out system to preserve freshness. Shelving time is tracked down to the day, with expiration dates digitally logged and printed clearly on all packaging. Retailers are often supplied with merchandising guidelines from Hershey's sales and operations teams, advising on optimal product placement to avoid heat sources and maintain visibility in high-traffic zones. This ensures not just product survival, but also consumer engagement. Meanwhile, Hershey's central data systems stay connected to the broader supply chain. Sales velocities from thousands of retail points are monitored using automated inventory systems that integrate with distribution algorithms. If Reese's products are selling faster than expected in one region, perhaps due to a seasonal promotion or viral social media trend, production forecasts and shipment routes are adjusted in near real time to prevent outages. Conversely, if stock is underperforming, the system can slow production or reroute product to a region with higher demand. But what truly sets Reese's apart in this final segment of its manufacturing cycle is its flexibility for innovation and customization, especially on a global scale. Reese's peanut butter cups aren't manufactured identically across every country. Although the core elements remain the same, formulations may be slightly adjusted to meet regional preferences, regulatory standards, or ingredient availability. For example, Reese's produced for the European market may contain non-GMO ingredients, or use different emulsifiers to comply with EU food safety regulations. Sugar content, fat ratios, and even packaging inks are tailored to local markets, and each international facility must pass regional audits to ensure compliance with both Hershey's standards and those of the target nation. Seasonal and limited edition Reese's lines introduce another layer of production complexity that extends into post-factory strategy. Every year, variations such as pumpkin-shaped Reese's in October, tree-shaped ones in December, and heart-shaped versions for Valentine's Day hit the shelves. These products require not only physical retooling, custom molds, unique wrappers, modified flow wrappers, but also adjusted production timelines to accommodate pre-holiday distribution. Most holiday variants are produced months in advance to ensure they hit retail shelves in time for the season, but remain fresh through the actual holiday window. To ensure holiday versions meet the same performance standards as core SKUs, Hershey uses accelerated shelf life testing. In these tests, products are stored at elevated temperatures and humidity for a condensed time frame to simulate long-term storage. The samples are then analyzed for fat migration, filling breakdown, wrapper integrity, and flavor degradation. Only those variants that meet Reese's strict internal benchmarks for shelf life, texture stability, and visual appearance are approved for full-scale seasonal release.